filmed in Australia. Well done. Okay, so let's work through Mandelbrot. So that's pretty amusing, and I guess now it would have been a different, we would have blog posts in the aughts or something, and now it would have been this frenzy of tweets with billions of people piling on and saying, splintering, and then Twitter trying to organize it. Oh my God. Anyway, okay. So we really care about the theories in the end, right? The people are fun on top, fun little surface pieces. So we're going to imagine we have a language with n words, which is going to be a lot of things that you'll see are pretty. Simon's model is very simple. This is also a highly simplified version of language. So, and it's going to be, this is the straight up zip distribution idea, right? There's going to be I words, and we'll have them ranked in terms of probability. And then this is exactly how really entropy works, Shannon's entropy works. We assume random production of words. It's obviously not true. Obviously it matters to us, composition of letters matters, but it matters in this model in an interesting way. It has to be an alphabet-based language that works for this thing. So this is stepping away from cities and all those other things that Simon was trying to kind of connect in as well. This is very language specific. So we're going to assume we have M letters, and then words are going to be ordered by shortest to longest, and the most probable one will be the shortest. And so you can look at this too, right? As short words, more frequently occurring and so on. So there's been lots of arguments about that, which was maybe surprising. Word cost, so we're going to have length of word plus a space. It's just going to be straight up length of word. Obviously it didn't matter for Simon's model. Real words don't use these all letter sequences, which is what will be allowed here, right? So for 2-letter words in English, it'll be 26 times 26, which is not really true, right? So for Scrabble, it's about 100 words. I mentioned Scrabble the other day. I think there are, depending on the dictionary you use, at some point, there was one dictionary that I remember, there was 98 valid 2-letter words. Okay. C and Q being an ox and X, really making the X just great. Okay. Vietnamese monetary units, very useful. Right, so they don't use all letter sequences, that's fine, right? So maybe real words basically follow this, right? So that shorter words are more common, yes. And there's some subset, maybe it's just sort of a ratio that we have to put in there. Words can be encoded in this way as well, that's possible, right? So we're not actually talking about the words, we're just talking about their encoding. And then, just yelling at each other. So, various objections. All right, this is just a kind of a gentle introduction, hopefully, to entropy, right? So, these are going to be the words. They're very odd words. So there's going to be encoded. We'll just have a binary story for our words. Our alphabet is binary. And then we have to have some space character as well. But for the words, it's going to be like this. So here's our most common words. So this could be the and of and. They're encoded in this way. And it's just a binary. We're just counting out in binary. Yep. And then the length of these, right? So this is length 1, this is length 2, length 2, length 3, and so on. That grows, and it grows logarithmically. This is log 2 of I. It grows slowly. So it's 1 plus log 2 of I. So this is a very rough, this is not a bad approximation for length. Obviously it's wrong when it's not a pure power of 2, right? So it works when it's 2 to the 3 here, and so on, right? So this is the idea that this will be the cost. So the cost is going to grow. So we're going to have these, we're indexing our words, and the ith word will have this cost. And we could get rid of the 1 as well. Right, so the 2kth word is going to have this length of k plus 1. So 2 to the power of 3 has length 3 plus 1. Right, 2 to the power of 2 has length 2 plus 1. And so that's true for all of them, as I said, and then we'll just interpolate and say this is roughly true. If we have m letters, then we're going to have a log m for this as well. Fine. All right, so this is a, not a bad thing, right? It's actual, like if you're typing this thing out, this is the cost, right? How many keystrokes to send this message. It's not clear how that works when you speak it, but this is not that bad. All right, so the model is going to be this. We've got a cost of the ith word. As I said, it's going to grow logarithmically. This means it grows slowly with its index. And if we add the space, right, each word's going to be followed by a space or maybe a period, but let's basically say that. So this will be the proper cost, but we don't have to worry about any offset. They've all got that, and we can do this. And we can also multiply by a ratio. This, if it's log based m, we can also rearrange it. You don't have to worry about this too much, but if you divide log e by the log e m piece, we get back to here. So this is just some general factor. So we could turn it into so we can say, okay, it's proportional to natural log. A natural log allows us to differentiate in simple ways. So that's good. So the total cost of this language, if we're randomly saying these things or we have these weights for them, there's the probability that the ith word gets used, then it's times its cost. And so we're just going to sum up this whole thing here, right? This is per word. So sort of an average thing that's happening. Okay? Ultimately, you're trying to find p sub I. What's the probability of the ith word? Okay, so that's just cost. And at the same time, we need a measure of information. So we're going to use, sorry, the first thing I showed you wasn't information, it was of course cost. Shannon's entropy. Right, so this is, and I'll talk, this is where I have a gentle introduction to entropy. This is the framing for it. It's usually written like this. It's not, there's some aspects of that which aren't great. I mean, it would be nice actually if this was 1 over pi in here, because that's really what it is, right? So it's a weighting of log base 2 of 1 over pi, which we'll talk about in a second. Von Neumann apparently told Shannon to call it entropy because no one understands that, and that would be better, right? That's like, this is a messy thing, and if you call it information, people will get the wrong idea about it. And in fact, in Shannon's original paper, I think in the second paragraph, he says, this is not about meaning. So, but information feels like, it connotes meaning, meta kind of way. All right, so, what this is the average number of bits to encode each word, because this 1 over p sub I, this log of 1 over p sub I, sometimes called the surprisal, is a measure of the average number of bits you would require to encode it, given that it occurs with this probability, right? So a word that appears half the time, you're going to assign you're going to say that's a 1, right? And everything else starts with a 0, because you want to distinguish that straight away, right? If half of your words are exactly the same, you want to use you want to use the minimal unit you can for that, and you would signify the start of your word would be a 1, and then anyone decoding it would know this is that word straight away, and they don't have to carry on. Right, so this is the saying what that is, and I have a few pieces on it, right? So, right, if it's a half, we need only 1 bit, right? So log of 1 over a half is 1, log base 2. If we had 1 over 64, so 1 in 64 words are this word, then we need, so this is 2 to the power of 6 on the bottom, so we need 6 bits for that, right? You imagine saying it's not this word, it's not this kind of word, it's not this group of words, or this group of words, it's this one. So you need this little tree that you're making of words, you'd need 6 branches for that. I guess 5 branches. All right. We can make a simpler thing here too. We can we can make it log e as well. Same kind of game there, so that we can differentiate. Again, it's proportional, so it's going to be. We'll put some constant, right? Minus g. Fine. But we've gone before. We had pi log of I plus 1 in here, and this is log e of pi. That's the big difference between those two. Okay, I know I'm going. So this is just a straight, normal Shannon entropy measure. We'll change it into a log base E thing. So we're going to minimize this function. We've got these n variables in it. We're going to call it the cost divided by the entropy. Well, yeah, we want to minimize that. Could be maximizing the opposite thing. So we're going to do this. And we have a constraint, right? That these probabilities have to sum to 1. They have to all be greater than or equal to 0. That's true too. And so the tension is clear, right? We have shorter words are cheaper, right? They cost less to say. Long words have more information, right? So we want to, there's a preference on top for the cheaper, shorter ones. There's a preference on the bottom here for longer words, because they'll damp this down. So that feels like it should have some kind of shape like this, right? They could all be really cheap, but that's not going to work out. All right, so you're going to make a Lagrange multiplier story. I probably should have asked you that. If you haven't seen Lagrange multipliers, it's okay. It is really, something you can work through. It's just a differentiation problem with many variables. Again, you don't have to have taken vector calculus or anything to get this out, but this will look pretty out of control, I suppose. Here's the function we're trying to minimize, and with Lagrange multipliers, you add the constraint function with a lambda, because what you're trying to do is I guess I can, of course I can do it on this. Yeah. So you're going to say, here's some constraint, right? So my variables your function has to list, you have to be somewhere on this path. And then there's some function of this space, right? So this is some space. There's some function on this space. You imagine like contours on this, of this function, right? So f increases this way, some function of, and it could be just terrain, right? So imagine this is a path around a mountain, and or on part of the landscape, and then this is some of the terrain. And you want to figure out, and the mountain's going up this way, right? So you're allowed to be on this path, and you want to find the maximum of this function such that you're on that path. So as you walk around on this path, there are these places, special places you get to like this, right here, and will be here, I guess, where the line of steepest descent and the normal to your path match up, right? They're pointing in the same direction. Doesn't matter what the length are, but they're just pointing in the same direction. And they're pointing in the same direction here. So here, your normal is pointing out in this direction. Let's do this. Put one here. Right, they're not matching up. Right, if you were standing there, you're on your path, you turn 90 degrees, so you look across your path, and then look at the steepest descent, it would be, not in the same direction. But you get to here, and that's straight up. So the idea is, it's going to have a funny looking contraption, but what you say is, okay, well, let's take this function, right, that this is the height of the landscape, and this is the constraint of where the path is, and we want those things to point in the same direction. And that will happen if we minimize all of this and then set it equal to 0, because we're going to say the normal to this thing and the gradient of this thing are, right, there's a 0 here, so that they have to be proportional to each other, and we don't care what that lambda is. Okay, that's you can look at it some more if you haven't seen it, but that's the basic idea. Or you can just do it, right? So here's our function. Put it all together, right? This is c divided by h. Sometimes you want to call it c and h, but that's the setup. And we have this constraint that the sum, I know that's a funny looking thing, but the sum of the pi minus 1, which equals 0. You always write constraints. You don't have to, but you write constraints as something equals 0. So you take this, work through it, some minor suffering, and you get out this result, right? So that the probability of the jth word decays as j, it's a j plus 1, but basically j to some power. So this is it, right? It doesn't come out of some other distribution or whatever. It comes out as a power law, decay. This is exactly the Zipf distribution, power law. So you don't have to, the slides are clapping. And then you do some sneakiness to get lambda out in terms of these things, and you figure out that this is equal to, whoops. Yeah, this is a proportional to, you actually figure out it's exactly this form, right? Right, this is an equal sign now. So it starts off at, for 1, it starts off at 2, 3, 4, right? So the internal piece here. And then this is some power. It depends on the information, the cost, this constant g. And we don't have to determine them exactly. We just need to, this is where we use our constraint. We know that the sum of these probabilities has to be 1, right? So the sum of these We can just sum over this, right? How do we want to do that numerically? We can do that. So this has to be true. So I'm just putting this stuff back in. So this is our constraint. Sum of probabilities has to be 1. We notice they're all greater than 0, which is good. So we're going to sum over this thing. And we'll just say that's alpha. That's our exponent alpha for Zipf's law. If you want, and you let n go to infinity, and you don't have to worry about this, then this is really the zeta function. Mathematicians love this thing. So it's a zeta function, but it really starts at 2 because j equals 1. This is 2, 3, 4. And that's something that's sitting in, lots of things. Lots of systems that you might use. And it's fun to draw zeta as well. But you don't have to worry about it. At this point, if you say, there are 10,000 words, you can just sum this up and say, which alpha gives me 1. If you let n go to infinity, then you roughly get alpha is 1.73. And this gives you gamma, right, 1 plus 1 over alpha. That's right, yep. If we flip back to the power law size distribution, and that exponent is too wide, right? It's more, we think, for Zipf's law, you often see closer to 1, which would be closer to 2 here, right? They're the two ways of looking at this, right? So Zipf's law should be closer to 1. Some variation, and then gamma is going to be closer to 2. So it doesn't quite come out right. And that's Mandelbrot's story. You can play around with this. You can say, well, the cost function we just made up, we can add an a to it. So that's a little game to play and see if you can mess around and tune this exponent some way.